Okay guys, now we're going to move on to type 2 integrals, type 2 improper integrals, and these are a little bit less obvious. Type 1 improper integrals had the negative infinity to start or the positive infinity as its upper bound. It's not so clear that this is improper just to look at it, but I have to remember the fundamental theorem of calculus, and the fundamental theorem of calculus says I can just apply that fundamental theorem as long as this integrand, as long as this function is continuous on the closed interval from 1 to 4. So if there's any problem with the x values between 1 and 4, including 1 and including 4, well then it's an improper integral. This function is continuous on its domain, but it has a problem at 4. If you plug in 4 for x here, you're going to have 3 divided by 0 to the 6th, and you can't divide by 0. The graph is going to look roughly like this. So this is representing an unbounded area starting at 1 and going to 4. So it's representing that area right there. So we've got an infinite discontinuity on the interval from A to B. And notice whenever that happens, your region is going to have, or the function is going to have an infinite range. The other problems we were looking at problems with are functions with infinite domains, but we've got an infinite range here. So that makes that area unbounded. So we're going to do the same thing that we did before. It's just a little bit harder to tell where the problem is. So I look at my integrand and I say, is this well defined on this interval? It's not. We've got a problem at 4. Since the problem x value occurs at the upper limit, I'm going to take the limit as b approaches 4 from one side. We're going to talk about which side that is in just a minute. I'm going to leave everything else the same. Even the integral I'm going to leave the same. I'm going to have a 1 there, I'm going to have a 3 here. X minus 4 to the 6th is still there. Exactly the same. But I'm going to replace that upper limit of 4 with a b. This is improper, but this is not. Graphically, what this is it's computing the area from 1 to b. So let's say b is 3. So b is right there. And then we're going to let b get closer and closer to 4, and notice we're getting closer and closer to 4 from the left. It turns out, whenever you're looking at the upper bound, if the x value that is a problem x value occurs at the upper bound, you're always going to approach that upper bound from the left, because the lower bound is fine and we're going to have that b and it's going to get closer and closer from the left every time. So I have pictures like this, and then we're going to go through the same procedure that we went through before. We're going to use the fundamental theorem of calculus to evaluate this guy, and we're going to use some Calc 1 skills to evaluate the limit, and then we'll find out what that is. So that is one type of improper integral, and we'll finish that one in a minute. We'll find out if that area is finite or not. But here's another integral. Trying to make up one that's actually well defined on the interval from -5 to 0. Let's do 4. Let's do the cube root of 4 plus x. Okay. First of all, you have to ask yourself, is this improper? And to do that, you need to think about this function. Is this function well defined on the interval from -4 or -5 to 0? I see I gave it away. If I'm on the interval from -5 to 0, I don't know exactly what that looks like. This is not a common graph. This isn't one we all study. back in college algebra or pre-calculus. I'm wondering, are there any problems in here? Any problems for any of those x values for this function? And we do have a problem. We have a problem at x equals -4. If x equals -4, we would be dividing by 0. So I have to split this into two integrals. I'm going to have one integral from -5 to -4. So that's our problem x value. Whoops, right there. And I'll have my integrand. Plus the integral from -4 to 0. The integrand does not change. And actually, I believe if we are greater than -4, we have a number over here, like let's say like -2. That's going to be a positive number. 1 over the cube root of a positive number is positive. So it's actually going to look a lot like the 1 over x graph. Different slope, same shape. If we're over here to this side of 4, like or -4, like if I plug in -6, well, 4 plus -6 is a -2. You can take the cube root of -2. That's fine. So this is going to be 1 divided by a negative number, so it's going to be negative. So even though this looked kind of more interesting than that one, it's actually not that much more interesting. The graph has got a very similar shape to the other shapes that we've looked at so far. But one thing that is interesting about this is that the problem didn't occur at one of the endpoints. The problem occurred at an x value in the interior. So you have to look at this integrand and you have to think about when is that function well defined and when isn't it well defined. I look at this and I say undefined at x equals -4. Then I ask myself, is x equals -4 in this interval? It sure is. So we have an improper integral. Now this is the integral from -5 to -4. So it's that one. It represents that unbounded area. That's supposed to be a vertical line, guys. I know it doesn't look very vertical. And then this one is the integral from -4 to 0. So we've got that right there. If one of these improper integrals diverges, then this improper integral diverges. If they both converge, you just add those together, and that's what this one converges to. Now this one, the problem is at the upper limit, just like on the last problem. And on this one, the problem is at the lower limit. Since the problem is at the upper limit here, we're going to let b go to -4. And whenever we're approaching the upper limit, we're going to approach from the left. Leave everything else exactly the same. Well, I mean, you could do the algebra on this because you're going to need to before you anti-differentiate, but you replace this with a b. So we're going from -5 to b. We're finding this area, and then we're letting b get close to -4 from the left. That's just this first guy. That's that right there. Now the second one, the problem occurs at the lower limit. So I'm just going to use a for the lower limit because that's what I do. Use a for the lower limit and b for the upper limit. I let a approach -4. Write everything else exactly the same. Now this, once I put the a there, is an integral that the fundamental theorem of calculus applies to. So I'm going from a, which is some number here, to 0. I find that. I find that area using the fundamental theorem, which is totally legal, and then I let a get close to -4, this time from the right. So if you're replacing your lower bound, this variable a is going to approach that number from the right. We approach b from the left and we approach a from the right. And then you evaluate this integral and you evaluate this limit and this limit, and if both of those are finite, then the sum of those is that net area. It's this area minus this area, and that's what that converges to. So we've seen you can have a problem at one of the endpoints. It can occur at the lower limit or the lower limit of integration or the upper limit of integration. Or it can occur on the interior. And then you have to write it as two integrals, two improper integrals. There's your first one and there's your second one. That one and that one. And then you write the first one as a limit. We approach the problem x value from the left. And then we write the second one as a limit. And we're approaching the problem x value from the right. And then we find out what those limits are. So that is the first step in all of these. You look at the integrand, see if it's truly improper, see if that integral or that integrand is well defined on that interval. And if it's not, you have to write it as a limit, either by doing something like this or doing something like this. You've got to rewrite this if the problem x value is on the interior of the integral. Interior of the interval, not integral. You have to do that by making it either the upper limit or the lower limit, and then evaluating these limits, evaluating these integrals instead. So let's look at one more. Now this one's not obvious, but it is an improper integral. In order to recognize it as an improper integral, you have to remember what natural log of x looks like. Natural log of x, remember, it looks like this. So if I replace the x with an x minus 2, it's probably been a while since transformations in college algebra, you take this whole graph and you shift it 2 units to the right. So it looks like that instead. That's y equals natural log of x minus 2. And taking that and multiplying by x, that's going to change it some. We could use Desmos.com or GeoGebra or your graphing calculator to figure out what this function looks like. But I know I can't plug in 2 to this. I'm okay to plug in 4. 4 is over here. The function's just, natural log of 4 minus 2. It's natural log of 2 times a 4 there. So everything is going to be fine at 4. But we're going to have a problem if we try to take the natural log of 0. You cannot take the natural log of 0. I'm just going to write it down. Or a negative number, not in the real number system. So this is improper. The problem occurs at x equals 2. So that's my lower bound. So I'm going to let a approach 2. Replace my lower bound with a. Leave everything else the same. And then say, okay, well, I don't know exactly what this looks like. I don't know what x natural log of x minus 2, that function looks like. I know what the log function looks like without the x, but I don't know how multiplying by x modifies it. But I do know that if I'm on the interval from a to 4, and I'm letting a approach 2, I'm going to be approaching 2 from the right. Okay. So then we evaluate this using whatever method is appropriate. Looks like integration by parts to me. And then after you're done applying the fundamental theorem, then you take the limit. So that is how we write our integrands with infinite discontinuities as limits. And be careful about things like this. How do I handle that guy? Well, it has a problem. It has a problem that x equals 2, right? But x equals 2 is not on the interval from 5 to 10. So this is a proper integral. It doesn't imply proper integral. It is a proper integral. Yes, the function is well defined. It's continuous on the interval from 5 to 10. So this is not improper. Just go for the fundamental theorem of calculus. Just do it. Here's another one you might see. Something like that. When is this one undefined? Well, I'm going to have a problem if x squared minus 16 is equal to 0. So I'm going to set that equal to 0 and solve for x by adding 16 to both sides and then taking the square root to the plus or minus square root of 16. So that's plus or minus 4. We're going to have a problem at x equals 4, and x equals 4 is on my interval. It's right there. So I'm going to write this as the limit as a approaches 4. And since it's a, since it's the lower bound, we're going to approach from the right. So those are our examples of writing improper integrals that are type 2 improper integrals as limits. And recognizing them in the first place. Being able to distinguish between that proper integral and an improper integral. In the next video, we'll actually work out some of these and see if they converge.